Brush up ourselves with, summarize whatever we did so far, and then we came up to that secondary name node, and we'll see a few issues with it, and we're going to go to a couple more new nodes, and then we'll see some high available architecture or configuration. Then we're going to quickly jump into MapReduce. We'll see some introduction, and from tomorrow onwards we're going to start writing a program. At least one. So tomorrow I'm hoping that we could at least start writing by at least finishing one program. So let's quickly get into it. So let's summarize what we were looking at. Yes. So Hadoop. So the big data was the actual problem, and there were challenges with the big data. And then we are looking at the solutions in the form of Hadoop framework. So the main core components of Hadoop is HDFS and MapReduce. And HDFS is the storage part, and MapReduce is the processing part. So these were the major two challenges with the big data, storing it and processing it. So far we looked at this master-slave architecture. So they're following master-slave architecture for the Hadoop cluster. And so the master here is the name node, which only maintains the metadata of the files. They are stored in the form of blocks on their data nodes. So the data nodes, so this is the HDFS part. The name node is the master, and data nodes are like the dumb terminals. So they only hold the data in the form of blocks, and they don't know exactly what blocks make up what files. But it's a name node which holds all the data, all the metadata, but it never stores the actual data. Actual data is always stored on name nodes, and it stores the data in the form of say this blocks and their replications. There's a small table, and it knows, where all these blocks are stored and their replications are stored, and what blocks make up to what file. So then we were talking about, so what if the name node fails, which is called single point of failure. If this goes down, everything goes down, because even if you are holding this data on data nodes, the actual data, there is no way we can actually recover the data, because all the metadata is gone, and there is no way that we would know what kind of blocks make up what files. So even though the data is there, it's of no use. Then we came to this secondary name node, which actually, earlier we were talking about this FS image. The image is exactly like that what we had with that VMware. So this was a CentOS image. Even when you are saving the image, it would be saving with whatever folders files you are creating. And if you share this image with someone else, and they would get the image updated with your folder names and your files. So this is exactly, the same one, but this is updated with whatever changes are made to the files on data nodes. A file is created, copied, deleted, and yes, there were a few more changes. Every change is logged into this edits log, and then periodically they are written to FS image. They are merged with FS image. So the issues were, that if the name node fails, the secondary name node would be having an edits log and an FS image, but the problem is if there is a time gap. So if the name node, goes down 10:45 and the periodical update was done at 10 o'clock. So there is a gap of 45 minutes. So the 45 minutes of data is lost. So, but the other issues are that it needs a manual intervention. So the rollover, failover or rollover is not straight away. So someone needs to get the data out of name node and then create a new node and change the DNS, the IP address in the settings file so that every data node or incoming requests are directed to this new node. So it needs a manual intervention, copying and putting everything back into the new node. So there is a downtime with this. So the recovery strategies are, so we can actually copy these things and put on a new node and bring it up, but there's also other ways to make the secondary name node as the primary name node, but we still need another secondary name node. And we're gonna look into this high availability approach, and we're going to go through a couple more name nodes, and then we will jump into MapReduce. So these are the issues with the secondary name node, as I was talking earlier. So the FS image file is not up to date. So it is done periodically. So if it is done at 10 o'clock and it goes down at 10:45, the primary name node goes down at 10:45. The 45 minutes of data updates are gone. So there is no automatic failover. So the switch of this name node with a new name node is not straight away. So there is no automatic failover mechanism at all. So, and at the same time, this name is a bit misleading. That's what they felt over the time, but they're still using in some places. They felt the secondary name node actually gives us an impression that okay, the failover, the switch is automatic, which is not indeed in reality. So they came up with new ideas, the Hadoop community, which are checkpoint node and then backup node and then highly available configuration. So the checkpoint node is, more or like the same name node, but it's only the name change so that there won't be any confusion. So no, it wouldn't give anyone the impression that actually it is an automatic recovery or failover. Then the backup node. So the backup node, they got some improvements. The biggest improvement, it also got all the functionalities of this checkpoint node. So from secondary name node and the same code base they were using for checkpoint name node, and they came to backup name node with the same code base, but here they had some improvements. So this one receives, backup name node receives a continuous stream of edits file changes. So if it is receiving this kind of the byte stream in the form of byte stream, continuous stream, so it doesn't have to go there and copy this file periodically, because this edits file is always up to date. So even it goes down the second, yes, probably it would be up to date by the second, because it's a byte stream. And it also holds the FS image in the memory, and which would be writing it back to that name node periodically. But the FS image is also up to date because it gets the edits log file by stream. So that now the primary name node doesn't have to maintain FS image, the kind of changes and write them to the hard disk every time. This also saves it some processing burden. So this whole process would become a little faster, and the one responsibility less for the primary name node, because backup name node is looking after maintaining the up-to-date FS image. So we come to this one last thing. As I was talking to Ramya, so if we dig deep, I mean, this is gonna go, I mean, a little deeper, and probably could stuck here, and from here probably it goes towards the administration, Hadoop administration, by setting up the cluster and configuring systems and configuring the total nodes and total cluster. So probably we would stop here with the architecture, and then we're gonna get into this MapReduce, and probably from tomorrow we're gonna start with the program. So I mean, they came up to this highly availability. So here, instead of having that checkpoint node or backup node, I mean, they got kind of two primary nodes, but that one node would be processing the request at any given point of time. But both can't be active at the same time. So only one would be, I mean, processing the request at any given point of time. But the active name node, here we call it, which is active for the moment, would be maintaining the edit log, which is in a shared folder and has access to the standby name node. And the another big improvement is all these, I mean, data nodes are configured with two primary nodes in the settings files. So they normally reach out to the first one, and in case if they couldn't reach to this first name node, and then they quickly try reaching the standby name node. And then the standby name node would start processing these requests. So the switchover is smooth without wasting any time. And the edits file is up to date. I mean, this is kind of the one they are using at the moment, but some of them they still have been using the older names and some old configurations. But from here, it is going to go more towards the administration than the development side. So I thought, okay, we'll start, I mean, we can start digging deep here and switch to MapReduce. But in near future, I was thinking of actually creating a cluster online if I could get my hands on any of these cloud computing platforms, if I could get in login. Then if I do it, and I would do, I mean, give you an update, and you could use that login for a few months so that you can play around. But everything else would be more or like the same, but you can switch nodes and check things. So let's get into this MapReduce architecture. So far it's more of the storage, and MapReduce is actually processing part. So this is where all this processing is done. But before we get into the actual architecture, let's brush up ourselves with that. What happens when we give a data set as input to this MapReduce. So technically we are loading a data set into our program, and we're going to run it on, I mean, store it on HDFS and run a program, a jar file, which is going to work on this. But before actually that fed to this program, the program is run, we were talking about parallel processing. So to achieve that parallel processing, the input file is divided into small chunks. These are called input splits. These input splits and the blocks are little different. This input split is at a logical level, the block is of more of a storage level, and even the hard disk level. So the file initially it is divided into input splits, a small chunks of files, and then they are fed to this mappers. So mapper is the program actually we're gonna write. Probably tomorrow we're gonna write the mapper program. So these small chunks are fed to these mappers. So the mapper program is run parallelly multiple times on these input streams. Does it make sense? So a file is divided into parts, say here 3 parts. So the record reader is a class which is part of this framework, which we make use to read from a text file, uh, read the data from the text file, and then that is fed to given as input to the mapper program. The mapper program is something we're going to write. And let's get into the architecture and a few more names. Here the new names are job tracker and task tracker. So here, I mean, if this makes sense, so far we are good. That we are going to get a big file. In real world, we're going to get 1 terabyte of file or few terabytes of file, and then we're going to make that into small pieces. And then that is given as inputs to mapper programs. But so these programs are run parallelly and this on these input splits. And who is going to look after these things? Because that name node's responsibility is more of storing blocks at a storage level. But this is of a processing level. It is a bit of similar responsibility, but this is of a processing level. Because parallelly, if there are say 100 mappers are running, so they're going to get 100 inputs, they're going to get 100 outputs. So who is going to look after, look over this process? So these are called job trackers and task trackers. So technically a job tracker would be only one, just like name node. And the task trackers are, there are going to be multiple of them. And the task trackers, as you guessed, they would be run on data nodes. And ideally they are run on where the data is. The way they allocate it, where the data is. But let's not worry about the allocation of exactly these mappers. But let's see, the job tracker and the task tracker is a little similar to name node and data node, but at a processing level. So the job tracker is going to assign tasks to the task trackers, and task trackers are going to work on these tasks. When they finish it, and they're going to reply back to the job tracker with the outputs. So if something is still running, or it's success or failure, everything is tracked by the job tracker. If the task trackers work is the kind of tasks it has been assigned by the job tracker to work on them. Let's dig a little further down and see exactly what it is. But before that, let's see what this map reduce, what its core responsibilities. And these would make more sense when we try writing programs and see the output, how it is generating, because it is going to give each task, each mapper with the percentage and everything when it is running. It is going to start at 0 and finish by 100. So it is tracked by this map reduce. So first thing, its main responsibilities are its resource management. Say if there are 100 task trackers, and say there are new tasks coming in, so what job tracker is going to do, assign these tasks to the task trackers. But the question is, there are 100, so whom it is going to give these task trackers to. So this allotment, so it has to check who is free. So I mean, there are basically the framework algorithms, they're going to check it. But when this is more of administration, these administrators, when they're setting this cluster, I mean, they're gonna set in this configuration files the maximum tasks one that node can handle. So the job tracker, what it is gonna do is, it is gonna check what is the maximum number of tasks this node can handle. I mean, these administrators, how they're going to, I mean, set this up by running few tests physically, and then decide upon the maximum number of tasks one could handle depending on the configuration of that node, hardware configuration. And so when the job tracker gets, I mean, few more new tasks, so the way it is going to decide is, if the data, the task tracker is already running few tasks. So say its maximum number of tasks are 10, and it is already running 4 tasks. So that means it has still got kind of 6 slots left. It can still allocate another 6 more tasks. If some other task tracker, I mean, the node's capacity is only 10 tasks and it is already running up to 10, so it can't allocate any more tasks. Or if it is only 2 free slots left, it can only allocate 2 and then move on to allocate it to the next ones. So the maximum capacity minus the number which is already running. So the resource management. So this is the resource management, how it is going to manage the resource, because if it is going to give the tasks to the task trackers which are already running few tasks, so it is going to bring down the performance. So it is going to look for free task trackers, the available task trackers, and it is going to assign it. And if it couldn't find, it is going to assign it to the already running ones, looking at the free slots. So kind of task scheduling and job coordination, and because I mean there are multiple tasks are running, and yeah, it needs coordination. And the job's progress, it is going to keep track of how the job is running, because if something fails, so it has to actually take the task and assign it to a different task tracker. So that comes under the same thing, tracking failures and reruns. If it fails, and it is gonna, I mean, give it to the new task tracker and rerun it again. So that's why I mean, it is important that it keeps track of how these jobs are running and their progress. So most of it is a part of that I mean, framework, because we're not gonna write any of those classes. This is part of the framework classes. But what we're gonna write is mapper classes and reducer classes. And sometimes it is called a combiner class, but we're gonna see what they are exactly tomorrow. So I mean, this is kind of the architecture. So from the client, here the request, I mean, goes to the job tracker, and the job tracker, I mean, a job ID will be given to it, and then the job tracker is going to assign this to a task tracker running on this data nodes, one of these task trackers, whichever is having free slots. And if a task tracker is running say 6 tasks, which is up to the maximum is 10, there are, I mean, 4 free slots, so it is going to assign to it. But when we are talking about the task tracker and the tasks, so this task tracker and tasks are run on different JVMs, Java Virtual Machines, because the whole Hadoop is, I mean, written in Java, and it runs on JVM. So this two things are run separately, the task tracker and the actual task, like a worker process. There is a reason. The reason is if a task fails, or if a program we wrote is having some memory leakage which could bring down, the task tracker, and there is no way that it could actually, someone could reply or report it back to the job tracker so that it could give the same job, it could run the same job on a different node with the new task tracker. So it runs these two things on two different JVMs, the actual task like work process and the task tracker. The task tracker is the one who looks after, say, these 10 tasks running parallelly. And then if something, one of them fails, it is going to report it back to the job tracker. The job tracker is going to take that one task and give it to the new task tracker, whoever is free, assign it, and gets it completed. But if they both are running on the same JVM, and if one of the programs, we wrote, if there is a memory leakage, and then the whole system would hang, and then the task tracker is down, and there is no one to report this back to the job tracker. Uh, that makes sense. So we're going to see more of this when we start, writing programs. Things would be a lot more clearer. So this is how it is going to happen on a MapReduce program. So the first step is the file is divided into input splits. Say, we were having that on HDFS user training HDFS1 folder. Actually, here should be one more slash and the file name. So we got test1. So slash test1. So the test1 will be divided into input splits. Say if we have 3 lines in that, say there are like 3 records, so it would be split into 3, and then that is fed to the mapper programs. So 3 of the mappers. So the mapper is number of mappers depended always on input splits, and the mapper is the job getting executed, which we write. And then there is one more phase which is called shuffle and sort, and then the output of the mapper is fed to reducer part. Reducer also another program that we're going to write, and the output of the reducer is the actual output we're going to get somewhere on this HDFS location. So say if we are giving it to user training and a new folder output, and these 2 files are going to created in that new folder, and in that whatever is processed in there will be in 2 parts. So now one last thing we will see for today. So we'll keep it short for today, and we're gonna start with full-fledged MapReduce from tomorrow. So the failures on MapReduce. There are kind of 3 types of failures on MapReduce. One is a task failure. So the actual worker processor which fails. So the task tracker is going to report it back to the job tracker, and the job tracker is going to assign it to some other task tracker and get it done. And this is not really a big issue. That's why I put it on green. And task tracker failure. This is called little serious, because if the task tracker fails, there is no one to report back to the job tracker about the failure. So this job tracker always keep in touch with this task tracker, and if it realizes there is no responses are coming from task tracker, then it is going to assign all the tasks under this task tracker on a different node to a new task tracker. But what if the job tracker fails? So someone from the administration team will have to work and fix it. Otherwise, we can't run any MapReduce jobs on cluster. So these are kind of 3 types of failures that could happen on MapReduce. So So this is from an old template I was using. So we'll keep it up to here, and we're going to run through quick, two things, because these two things might sound a little similar.
Srinivas Ramya here.
Yes.
Before we go that, I have two questions.
Yeah, go on.
Could we go through quickly?
Yeah.
So in the HDFS system, when you are explaining the architecture, you said that so it will the main system will manage
Yes.
the map,
Yes.
right?
Yes.
That will be shared with the secondary system.
Yes.
So, in the case of the failure of the first system, how will the shared drive will be available for the secondary system? It will not be available to the secondary system, right? And how would it take the would it be ready with the local copy?
Oh yes,
It always copies the local thing.
actually, yeah, that's a good question. There are kind of two or three types of failures. One is if only the power goes down, we can
Mm-hmm.
still have access to this hard disk. So that's one way. And
Okay.
if the hard disk crashes, then there is a problem that
Right.
we would lose the data, because this backup name node would have the update, but it only gets it periodically. As we were taking,
Mm.
the example of, so if it is getting that update every 1 hour, say at 10 o'clock, it gets an update from the primary name node. And then at 10:45 the primary name node fails. And the secondary name node, it is supposed to get update at 11 o'clock, isn't it?
Mm.
So this
Mm.
45 minutes of data is lost. So that's why we came up to this high availability, which is the kind of a solution, later they came to. So they were going through all these things. They finally, they came to this one. You mean if this edit files, if they lose this edits file?
Yes. So
Okay,
this is
so
primarily managed by the active name node, right?
yes,
Edits will
yes,
be managed by the active name node, and that will be shared as in a shared drive to standby name
yes,
node.
but
So active name,
that's
yeah.
right. So this shared one is, almost update, all the time in this standby name node. So this
Okay.
edits log is a really small one. So getting, constant updates is not a big deal. So it is always shared with it. So it gets always update of this edits file. So this is shared among, you can think of it as both of them will have a copy, and it is updated. And at the same time, the data nodes will be sending, I was talking about the heartbeat signals.
Hmm.
So they would be sending this to both the name nodes, which they would have update of what block, is of what file. So here it would be, they both would be having the same updates, but at any given point of time, only one node would be processing the request. So this highly availability configuration, you can think of it as that both the nodes would have all the data up to date,
Hmm.
but only one, at any given point, one name node would be processing the request. So even this block locations, everything, every 3 seconds, they would be sending a heartbeat signal about whatever the blocks they are holding. So they would be sending it to both the nodes. So both the nodes would have kind of up to date of
So,
information. Yes.
so is it our, whoever is the administrator, his responsibility to configure which node will have the priority to update the edits log? And what is
Yes.
the, how would be available? So both of the active name node and standby name node have the local copy of from these edits, or
Okay. Uh, it would, this is a shared copy.
yes.
Yes,
Uh,
it would be having in its drive, but it would hold this in the memory, in the RAM. So it would have one updated one all the time. So it would have an
okay.
access, and then it would have an updated everything in the RAM. So it would always hold this its own copy. And if that goes down, it is going to start processing it straight away, because even reading
Mhm.
from this but hard disk is going to take a little more time.
Yeah, okay. So would there be any default setting for the standby name node priorities, or we need to configure? I mean, administrator will give the
So
configuration.
yes, I mean there are default settings, but the administrators, I mean, would can make few changes, but that would go is more of that administration work. So if we could
Okay,
get
okay.
the cluster set up and we can have a look into it.
Yeah, okay, okay, okay.
Okay, all right.
Okay.
Yeah, one question over here. The edits log, right?
Yes.
It will have uh, all the block addresses of where exactly which block is located on the data
Uh,
nodes.
yes, edits log is not the complete information about the exact block location and everything. So they both would be having their own FS image. So only edits log is about the changes. Say every 3 minutes, whatever changes are updated into edits log. So sorry, yeah,
What?
not even every 3 minutes. So if there is a change, if a file is deleted and that is written into edits, it's a log file. So
Okay. So when we are talking about processing, parallel processing and everything, right?
yes,
So we are taking the input files and we're churning the data and we're getting an output. So would
correct.
the edit file have that particular data also in it? That where
Uh,
exactly is the output? How much was processed?
yes, yes, it would have about the locations, about the blocks.
About the block. So other than block information,
Yes.
what else is stored in edits log?
Basically, we were talking about metadata of if the file is created or moved on to, I mean, HDFS. Uh, so what are the permissions? Who is the owner of the file? It's like if we right click and see the properties of I mean, any file, it is going to give all the properties list. This is the metadata of this file. So it will hold all the metadata, but there's a small difference between this FS image and edits log. So FS image is the exact image of everything. Does it make sense? So
Yeah.
FS image is the image of the image actually, I mean, you got with the VMware.
Okay.
But edits log is a file which is gonna record any change to that FS image. So if you have actually created a folder with your name on that image, whatever you got with the VMware, then this change is logged onto this edits log. I mean, this is as an example I'm saying. So
Okay.
if you created a folder, then that update is done in edits log. And you created a file test1, that update is done into edits log. And then the actual image is right there, and these two changes are merged to the FS image this is holding and the FS image this is holding.
Okay.
So that is periodically. So updating the FS image is gonna, I mean, little time taking process. So instead of updating the FS image every time for every single change,
Got it.
we're gonna keep
So
this is like a buffer. Edits log is like a small buffer.
okay.
Makes sense?
Yeah, makes sense now.
Okay, excellent. So I was talking about just one more thing to give a little clarity. So we were talking about here two things. So this is maybe we could do the other way around. New one. So yeah, so far we talked about these two things, and there are a few similar things in them. I just want to make sure that we are on the same page. This is HDFS, and so we were talking about name node, data node, and that secondary name node and other active standby name nodes. They fall under this layer. There are two layers we are talking about here, and this so we are talking about task tracker, job tracker, and task tracker. So when we say, so this part probably we have better idea. So this job tracker, task tracker, we have seen it today. So the job tracker, when I say it is not actually the name node. So most of the times it is a good idea to have a separate node for the job tracker. But the task trackers, they are run on mostly data nodes, because it is a better idea to run this that one job where the data is available. So if this one task is gonna perform on that so and so particular data, part of the data, whatever is in the input split, the one input split is made up of few blocks. So the job tracker is actually going to check whether that part is available. If that data node is available to run this task, it is going to actually alert to it, so that the task is going to run where the data is, so that it doesn't have to copy it from one node to another node. So these are basically two layers. One is HDFS. In that we have this name node, data node, and the another layer is MapReduce, which is going to run on top of HDFS. We have job tracker and task tracker, and the job tracker is going to oversee this. Task trackers, and the task trackers are going to oversee worker process. Does it make sense? Because we're going to see more of it this tomorrow. This MapReduce. So we just started with the MapReduce. That's going to take 2 or 3 days at least, and we could run even to an extra day. So we're gonna, shall we stop it here, and when we come back tomorrow, we're gonna directly get into MapReduce. Any more questions?
So this name node and data node, is it common for the entire process? Like in HDFS, we assume, so we split into 5 areas. We have 5 clusters or 5 sub data
Yes.
centers.
Okay.
So data centers, I'm saying. Regional data centers. So
Okay.
how do gets connected? So for the entire thing, we will be having one name node and one data node, which is the main server kind of thing, or we will be having again subsystems, and to manage again to map this, do we have a different architecture kind of configuration?
So for all cluster, it is going to be one name node. So even if it is, at a different places, but they are still gonna have a global view, because it's a distributed one.
Okay.
Yes.
So basically, administrator will take care of the configurations. As a programmer, we no need to bother about those configurations.
No, we don't. If we have an idea, it's a good thing, but we don't really need to worry about that administration side, because we have seen already, I think, enough of that, architecture, but probably if there is a chance, we could get into some settings file and we see. That should be good enough, and if we get a chance, but not now, they would make more sense if we actually get into a cluster, because we are at the moment working on a single node setup.
Yeah, and as a programmer, we just need to know the managing of the files. How do we, like, what are the Linux commands we go through?
Yes.
Like making a files and removing files, these kind of things. Okay.
Yes, I mean these are the kind of basic things, but once we start running these map reduce jobs, you will have a better idea actually, I mean, why we need to know what, exactly what are
Oh,
the things we need to know.
okay. Would there be any locking systems on the files while they are getting edited or something like this, or
Yes,
that is like any RDBMS?
once you copy an HDFS,
Mm-hmm.
HDFS is called that kind of immutable. So we can't, I mean, change it, rename it, or do anything. We can't edit any file.
Okay.
So
We
unless
cannot edit the file name, but we can still edit the file content, right?
no, we can't. We won't be able to.
We won't be able to edit the
No, it's
file.
only read only. After that, it's only read only.
Okay, okay,
So
okay.
the VI command, it won't run on HDFS. So it's only the cat. So where we could actually just view the content, we won't be able to edit it. It's only if you want to edit it, the only way is that copy the file back to our local system and edit it and remove the one on the HDFS if you want to replace with the same name and copy it back to the HDFS.
Okay.
So it's kind of a most completely locked.
Okay, okay, okay.
All right.
So while one is reading that file,
Yes.
if other is try to delete, would there be any kind of mechanism to stop that?
Uh, so I didn't come across, I mean, this part because, I mean, if
Okay.
you are talking about programmatically,
Yes.
okay, programmatically, I didn't come across this one. So I'll try to, I mean, check that out and I'll give you an update because there should be one part of this framework because one is trying to read and other program is trying to delete. But I mean, I haven't come across a situation where a program would try to delete it.
Okay.
Okay, maybe that could be the other reason. So I didn't come across any situation that, or think of any situation that where a program would try to delete a file from the HDFS. I mean, there are, I mean, ways to recover it, but you are talking about at the same time, if one is trying to read and trying to delete it, I mean, technically it's going to, I mean, throw an exception if it deletes it, but so I'll have to check it still if there is a
No, okay.
mechanism to stop it,
Yeah,
if that happens
you're fine.
automatically. Okay.
Yeah, I just am myself just thinking loud whether we need to cover any other topics under this. Thank you.
All right. Okay, that's okay. I mean, yes, if anything comes up, yeah, please let me know. Probably I would also, yes, I mean, get it updated. I mean, part of it. Okay. Yes, guys. So shall we stop it for today and catch up on the same time tomorrow with the map reduce and with a basic program. Okay. All right. Cheers.
Okay.
All right. Thanks.
Okay, thanks, sir.
Thanks, Srinivas.
Thanks, Ramya.